Okay, good morning. So in this short lecture, I will take care of one, hopefully last, piece of mathematics that we need to have covered before we sort of summarize all of the information we have discussed about the structure of quantum mechanics into a set of rules that I will provide in the next lecture. But in this lecture, I would like to deepen a little bit the concept of what we briefly discussed as the Dirac delta function. Because this is a symbol, or let's say, let me define it this way. This is a symbol that has already appeared in these lectures and will keep on appearing in the forthcoming lectures. And I'd like to sort of elaborate on this idea a little bit further for all of us to have some sort of sufficient level of understanding of what it means. So, as usual in this course, I will not take the formal approach, which would drag us afar from the main purpose of the course, but rather what I consider a good compromise between being sufficiently accurate and sufficiently pragmatic. So, as far as we are concerned, a delta function is a suitable generalization of Kronecker delta to the continuum. So what does it mean? So it's very simple if you have a discrete set of discrete labels. So you have states labeled by an index 1 to n. It's very simple to define the following object. It's a two-index object, so it looks like a matrix. And this object is 1 when I is equal to j, and 0 when I is not equal to j. We've seen that already in the course. And this is the Kronecker's delta. Now, since it has two objects and there are discrete indexes, I can represent this mathematical object as a matrix. And what kind of matrix is it? Well, it's a matrix which is 0 when the two rows and columns labels are not the same, so outside the diagonal. And it's 1 on the diagonal. So, I mean, the Kronecker's delta is just the identity. Very good. I want to, so far everything is really embarrassingly simple. There is one slightly less trivial property of the Kronecker delta that will become at hand handy later on when we discuss the delta of Dirac. And it's the following thing. Suppose I have a sum made by contracting some index, and I have my delta ij and some matrix ak, for instance. And suppose for instance, I'm summing over j. So you see, I have the same index j that we take a different colors that is summed over, and this index appears also in the Kronecker delta. Then the statement I'd like to make, and I think you can convince yourself quite easily, that the effect of having a sum involving the Kronecker's delta is that of canceling the sum, because basically what this is equal to is ik. So the overall effect is that of taking away the sum, I'm using a different color here, taking away the delta, and replacing this index with the index that the Chronicle delta sets equal to. So in this case, I. If this property doesn't sound completely familiar to you, let's make an example that will clarify it. And hopefully will convince you that this is somewhat a trivial statement. So I have sum over j. We say delta ij aik, where now I is a given index. Any index that we want is fixed, is not being summed over, and so is k. So I and k are being fixed. If we want things to be, specific, let's assume I is, I don't know, pick a number, 3, and j is, and k, let's pick a number, is 6. And let's suppose that the sum goes from 1 to n, where n is equal to, why not, 6. I'm just picking 3 random numbers, right? I mean, there's no particular reason why I chose these 3 integer numbers. So just, for sake of example. So what this sum is actually doing is saying that I'm summing from 1 to 6j delta 3j a j 6. I just, use these 3 pieces of information. So I have, delta 3 1 a 1 6 plus delta 3 2 a 2 6 plus delta 3 3 a 3 6 delta 3 4 a 4 6 delta 3 5 a 5 6, and finally delta 3 6 a 6 6. Now, as you can see, all of these terms in the sum are redundant because this is 0, this is 0, this is 0, this is 0, and this is 0. So whenever you have a delta function, delta Chronicle delta, the sum involving the label that appears in the Chronicle is actually redundant because it will kill, it's a sum of 0, except in the only case in which the 2 indices of the Chronicle deltas happen to take the same value, which is, since one index is 3, is when j is equal to 3. That's this element here. So altogether, all of that, and in this case, delta is equal to 1. So whatever happened here is 3 6. So I can skip this intermediate step in which I am spelling out all the terms in the sum and say, okay, this sum is redundant. I can take it away. And all I have to do is to replace j with the only value with the value that appears in the delta function, in this case, 3. And so simply write 3 6. And if you generalize to arbitrary indices, there's nothing specific about this particular choice of indices, then we go back to the theorem that I was just stating before. Sum over j delta ij ajk is equal aik. Very good. Now, so let's now move one step forward and consider the Chronicle from Chronicle delta, the transition from Chronicle delta to Dirac delta. So in quantum mechanics, we are used to seeing that oftentimes we have states that are not labeled by a discrete set of indices, but rather they are labeled by, in principle, continuum set of indices or continuum variable. That's the case, for instance, of a wave function, right? The wave function can be viewed as the projection of the continuous eigenstates, basis of eigenstates of position operator of the quantum state psi. Now, you can discretize the continuous set of states on the lattice and making x a discrete variable. But in general, you might be in a situation in which x actually is not discretized on the lattice, and formally, you want the formalism that accounts for the fact that x can be any point wherever you want. Now, this means that, you know, we already encountered this problem that when I define the orthogonality condition, if xi, xj are 2 points on a discrete lattice identified by 2 different points, then clearly this can be represented as a Kronecker delta. The orthogonality or phonormality conditions becomes simply a Kronecker delta. But then we wanted this condition to be happening, also to be generalized to the case in which x and I and j are not, you know, the arguments are no longer on a discrete mesh, but they're in the continuum. And remember, what we were just sort of mumbling was, we want something that resembles the property of the Kronecker delta, but takes into account of the fact that, you know, the argument of the function delta, you can think about it as having 2 indices, x and y, or taking them to have a difference between the indices and the argument being to 0. These are equivalent notation. And this notation, this is a generalization of the Kronecker delta where x and y play the role of the labels. And in this notation, it's more like saying, unless the labels are equal, in which case the difference is 0, the function delta, or whatever delta is 0, and it's not 0 only when the arguments is 0, which means when the 2 labels are equal. These are 2 equivalent ways where you can use to write down this constraint that, you know, you have 2 objects, and you want these 2 objects to be the same for this function to be non-zero. So the idea was that basically delta function is something like it's finite only when the argument x minus y goes to 0. And it's 0 everywhere else. Now, however, we want this generalized function, delta, to preserve the same properties of the Kronecker delta. And one of the fundamental properties of the Kronecker delta comes from the theorem we just discussed. If I take delta sum of I or delta ij, this is actually 1, right? So, because all the terms in the sum are 0 unless I is equal to j, in that case, delta ij is delta 1, 1, which is 1. So now, if I go to the continuum, this basically tells me that the integral of the delta function should be 1. Now, or stated differently, if I have even 2 indices, you know, I can even say this. The previous equation was the case in which y was 0. But in general, I can put a y there and say, okay, for every y, just as much as for every j, this is true. This is true for every y, and this integral is supposed to be 1. Very good. But if my definition of delta is something that is 0, strictly speaking 0 everywhere, except in a point where it's 1, that's a reasonable function you can always define. The only problem that a function that is strictly 0 everywhere but equal to 1 in a point does not obey this normalization condition here, because the integral of a function that is 0 except in a finite amount of points is by construction 0. So the area underneath this curve is 0. So clearly this does not provide a good continual representation of the Kronecker delta because it violates this important property, which you want to be used. So the way you define a continuum generalization that, in essence, satisfies all the properties of the Kronecker delta but applies to continuum index, is that of taking the limit of functions that are very peaked around the origin, but whose height changes together with the width as I take the limit in order to make sure that the area remains 1. For instance, the simplest example is like you take a step function with size delta and height 1 over delta. Right, and then you say, my function is not 0 everywhere, but 1 in a point, is 0 everywhere until a small square of size delta and height 1 over delta. Now, the area underneath this region is obviously 1. So you obey this property down here. And then all you have to do is you take the limit. The delta goes to 0. So what you do is squeezing the function to a smaller constraint, but let it be higher. And in practice, you stop whenever the limit, whenever delta becomes smaller than any other scale, then it doesn't really matter what you choose. You can choose different representation. You can choose Gaussian representation as well. You put the sigma here, finite variance, and of course the normalization comes with 1 over 2 pi sigma. So whenever you make the Gaussian narrower and narrower, you keep track of the fact that you have to rise up its normalization to maintain the overall area under the curve. And then again, you take the limit of a sigma that goes to 0 until you're so small that you don't care to make it even more small, even smaller. Now, these are all equivalent representation of the delta function. They all convey the same message. You want a squeezed function with a height so that in the end, the area is always 1. So the correct definition of delta function that basically is independent of which specific definition of delta function you're using is the one that exploits the property we wanted to maintain from Kronecker to delta. So let me explain. Remember, in Kronecker, we have this important result. So all you have to do is to remove the sum and replace the index. Now, when you go to a delta function, when you have like delta of x minus y a of x, we are in a similar situation. Then you want this to be equal of a of y. So basically what happens, you have your function a, you multiply by a function delta that has this property and 0 only of y. So the product of these two functions is basically 0 everywhere because you're multiplying the value of a times a number that is very small, except in this point where you're multiplying a in the neighborhood of this point, you're multiplying a by a function that is very large. But because of this normalization property, that's the property you want to respect. So in essence, a delta function you find in books, its definition is whatever object function delta such that when you perform the integral with respect to x, it removes the integral and you substitute the value of the integrand with the value y that is set by the delta. So I don't care what kind of definition you want to use, whether you want to take the pragmatic idea and think about the delta as something that is basically a narrow function with a height that takes into account of the fact that the area must be 1, or if you want to take the most mathematically general approach, that is my object, such that if I multiply by a function and take the integral, it gives me the function in the point where the delta function argument gets to 0. As long as you understand what we talk about when we refer to the delta function. Okay, if you have any questions, let's discuss this on Wednesday's lecture.